And we are live. Welcome everyone. Happy Saturday. This is the code hour from XTechnologies. Today we're gonna continue talking and looking at our amazing expert Alexey.
Yes,
he's
yes, I
gonna.
am.
Yeah, sure. Yeah, so a couple of weeks ago he started presenting his work, which is about computer vision and neural networks. So today it's the part 2, and we're gonna jump to the next stages of his project.
Yeah, thank you, Igor, for introducing me once again. I'm Alexey. If someone forgot me already, I was the host of not the previous coding hour, but the one before the previous one. Well, we finished, we couldn't finish last time because there's just so much coding to do. I hope this time we can finish, or at least get a lot closer to finishing our project. And I guess I can show you my screen right now. Yeah, and we can continue writing code for our application. Previous time we were blocked. I couldn't display an input for our application. I can even show you what I mean. So right here we can draw, we can paint, but there is no input right here. And I want it to look like this, actually. I can even show you. Our final result for this application should be like input here. We should be able to write something down here, and we want to show an amount of images that have been saved for this label. And I have actually figured it out off stream what went wrong, and it's actually this stuff right here. We want to update our input when we paint our like when we paint everything in our application. So I forgot this line right here. We want to update our input, and we do also want to send events as argument for input, so that it can so that it can understand which keys I type. And if I save it and try our image generator once again, here it is. Here's our input. All right. So what else do we need?
Alexey, just sorry for interrupting.
Yeah.
For the sake of nice stream, could you please share what you're doing to Google Meets?
Oh, sorry.
Yeah, otherwise I see it only with a delay. It's
Oh
my
yeah,
bad.
yeah. I forgot. Sorry, Igor. Can you see it? Can you see it right now?
Yeah. Thanks a lot.
So we have our input, and well, we want to utilize it somehow. So what I mean by utilize it, we want to save our images for a certain label in like different directories. Right now we have a single folder called created images, and we save all our images to it. But we want to create different directories and save images to them instead. So for that, I already have a variable called current directory, shortened as cardir. And we do also have a count variable that counts all the images inside our current directory. So I think we can uncomment this function, this method right here called change directory. And I guess it actually should work. Yeah. Oh no, it shouldn't, because right here we only assign a variable to our current directory. But we want to first create this directory, and then we want to update our count variable so that it shows the amount of images in this directory. So for that, let's create this directory if it doesn't exist. So if this directory doesn't exist, we want to create it. All right, and then we want to update our count variable. For that, we do images in this directory, and then we update our count variable. All right, we've updated our count variable, but we do not display it yet. And we want to do it in this method right here called draw stuff. I guess I can just copy paste my code from the first application that I made and explain it to you. So right here we have a text with this font that we've defined in our initialization function, and we do render a count, self.count. We do not want anti-aliasing for that. I don't know why it is even an option, like right here as a second argument. And the color for this text should be red. And then we just add to our screen this text, and this is just to help our app understand in which position should it be placed. And well, let's actually try to run our application once again. All right, we see 0. Yeah, that's not actually correct, because our current directory is created images, but we have not yet called this method yet, so that it can update our count variable. So if, for example, I try to type, well, let's say square. Oh, and one more thing, I typed it, but I haven't yet called this method once again. I have only written it down. We have to actually call this method, and let's see where is the right place to call it. So once we typed our label and pressed enter, I want our application to create a directory for that label. So it should be mouse motion, mouse button. No, it should be something about pressing an enter button. And for that, I'm just going to write case g.keyDown. Oh, it's actually pg, not ph. Match event.key. And in case it is enter, we call self.change directory. All right, that sounds correct. Let's just place it on the next line. Let's check it once again. So first of all, we close our application and start it once again. All right, we still see 0, but this is because we haven't called this method yet. So if I type square here, all right, see, square directory has been created. That's good. But what about this 0 right here? Well, we do not have any images under this directory yet, but if we try to create one, for example, let's draw a square and press middle mouse button. We see a square under this directory. Well, it's not really a square because of this this duluth right here. I think we can delete it, but we see that count variable has been updated as well. This is good. What if we try to create another square and save it once again? All right, we see a second square right here. This one is a better one, and the count variable has been updated as well. What if we want to create another directory, for example, 1? All right, I typed 1 and pressed enter. The count variable has been updated, and we see another directory in our created images folder. Let's draw a 1 quickly, save it. Here it is, and count variable has been updated. What if we change our directory to square once again? All right, we have two images underscore directory, and it says that it is correct. We have 2 images. All right, so I think we can delete.
Unit tests work.
Yeah, we've tested our application. I can leave these directories right here, and let me think what we have to do. I think we actually finished with our application called image generator. We don't have to do anything more. So all right, we have images. Let's move on to defining our model, our convolutional neural network. Let's create another file called model.py.
And Alexey, just a couple of words. So this model is supposed to recognize the image, right?
Yeah, it should be able to classify them. So
Classify.
you see, we have 1 here and the square right here, but our neural network doesn't know about these labels anything yet. And we want to make it understand which image is it. Is it a 1? Is it a square? And later on, we will create another application in which we will test our model. We will write down some, well, maybe a number, maybe we'll paint some figure, and our neural network should give us the classification result. What is it? So we have a model here. Let's import torch.nn as a neural network, torch's neural network module, and then just define our network module. So we have to start with initialization. Oh, I don't want this arrow button right here, but thanks nonetheless. It's actually super.net, and then we pass self. So why did I choose a convolutional neural network? I mean, there are so many designs for like for neural nets. This is because neural networks are generally good at image classification problems, and not only image classifications problems, but classification problems generally. So so basically it looks like this. This is called the convolution. We have some input image, well, maybe not an image, but rather some input, and we have a lot of kernels. Well, you can call them filters, and we just take one small batch of information, like local information. This is in this exact example, it is 3x3 batch, and we multiply it by our kernel, and after we cycle through all the pixels right here, we get another output, which is called the channel. And essentially just imitates how human's brain visual cortex works. There are some differences, like some fundamental differences, but our visual cortex recognizes edges and then combines it into shapes and objects and faces and all other stuff. So this is why it is, well, this is why it is good for like classification problems, and especially image classification problems. There are like an early examples of fully connected neural networks that were used for image classification problems as well, but these are not optimized for classifications problems yet. These are like some old examples of how things worked.
Also, yeah, they are much heavier to train.
Yeah, and this neural network is heavier to train as well. Yes. So we've defined the model that we want to use. It's a convolutional neural network, and then let's actually write down some code. So I want to define our convolution layers. So let's call it self-conv1. I'm going to use PyTorch's convolution layers. convolution 2D, since we have a like 2D image. In channels is going to be 1, since we are going to, for an input, we are going to have an image, like a grayscale image. And the grayscale image only has one channel. Out channels, I'm gonna put it at 8. There's like not really like anything that defines what a good out channels is. I just don't want our neural network to have like a billion of parameters, because it's going to be easy for it to be overtrained, and well, it's going to take like a lot of time to train it. So I'm just going to put it as 8. Our kernel size is going to be 7, and when I write 7, it actually recognizes as 7 by 7 filter. So you see right here, kernel is actually like a 2D array as well. But if I write it just as a single number, it's going to recognize it as a square 7 by 7. I'm also going to have a padding of 3, well, 3 by 3 actually. Padding is something that's going to be added to our initial input, a bunch of zeros right here, so that it is easier. Well, it actually helps because it's going to be hard to explain for me, but every pixel in our original image is going to weight the same, essentially. And we don't want any bias, because we are going to use an average pool later on. So let's define it as false, and we will also want to padding mode to be zeros. So what this padding mode is doing, well, when we define padding for our image, it's just going to create a bunch of columns and rows in addition for our input image, and the values for these columns and rows are just going to be 0. It's like a black background for our image. All right. Oh, we don't need this sign right here. Then what I want to do is to, well, after this convolution, we are going to have a bunch of filters. We will actually have 7 channels. We have, oh no, wait, oh my god, I'm completely lost. Out channels is 8, and we are going to have 8 output channels. But what is the size of these channels? Like, we have an original image of 64 by 64, is, if I remember correctly, yes. So we have a 64 by 64 image as input. After this convolution, we have 8 channels, but what is the dimensions of these channels? Is it 64 by 64? Is it 32 by 32? There is an easy formula. Formula to, remember, I guess, which helps us identify the dimensions of our output image, output filters. And if you use it, we're actually going to know that the dimensions of our channels is 64 by 64 once again, because we went through like one row by one column by column with padding, and we got the same output dimensions as we had before. And we have, all right, we have 64 by 64 image, well, a channel, and we want to, somehow compress it, because we want to end up with only like a few results. Like we have 1 and a square in this example, so we want to end up like only with 2 output, labels. And for that, I'm going to use an average pool. So let's define it. So that pool1, average pool, and I'm going to sample a 4 by 4 like patch of our image. And what it essentially does is that, well, I think we can even average. yeah, there's the great image. So we have our 64 by 64 filters, and we're just going to cycle through them. And in this example, there is a 2 by 2 patch, but I defined my patch as 4 by 4, and it's just going to take an average of the numbers in this patch, and it's going to compress it only to a single number, which is an average of these numbers. And well, we had a 64 by 64 filters. Now we have 64 divided by 4 by 64 divided by 4. So we have 16 by 16 filters right now. And then I'm going to use another convolution layer. In channels is going to be 8. Well, because we've defined it right here as out channels. Our output channels is going to be 16. So we've increased our channels, but decreased the dimensions of our channels. We're going to define kernel size as 5 this time, just because our original images are just so much smaller. We're going to define a padding as well as 2. We don't want any bias, and our padding mod should be zeros. All right. So right now we do also have 16 by 16 channels, but this time we have 16 channels. We have 16 channels, 16 by 16. And then I'm just going to use another average pool to decrease the amount of information that we have. Average pool 2D. And I'm going to, I guess, use another 4 by 4 patches. And after this average pool, we will have 16 channels, 4 by 4. All right, I think we can use then another convolution layer. In channels is going to be 16. And output channels, well, it's going to be, well, I could say we are going to set output channels as 32, but we should end up with only two values for 0 and the square. So we already have like 16 filters 4 by 4, and we do a convolution layer, and I just think I'm going to compress this information just down to these these two values. So output channels should be 2. We want our kernel size to be 3. Our padding should be 1. We don't want any bias once again, and our padding mod should be zeros. So what's next?
Alexey, just a stupid question from my side. So you're kind of manually calculating all these inputs and outputs in between the layers, right?
Yes, I do that because I know I've written this program before, but you can find like information on the net pretty easily of how to define these values. It's not rocket science. You don't have to be as strict as I am with this like output channels, in channels, and kernel sizes, paddings as well. It's just that, I mean, I've done this before and I know, well, the best way to do it. And I'm just trying to explain you why is it the best.
Yeah, no, it's totally nice. I was actually about to ask, is there a way in PyTorch to help you kind of understand
I think it's just going to throw you some kind of error if you try to run this. If you'll try to run this like feed forward function method for this neural network, you're just going to end up with an error that says, well, some input just cannot be multiplied by some other input.
I got it. Yeah. So on like coding time, it won't give you a hint.
Yeah.
On them.
Yeah, that's it.
Okay. Cool.
And let me just think a bit. All right. So we have 2 channels. We have a kernel size of 3, padding of 1, and we are going to end up with oh my god, what we're going to end up with. We're going to end up in 4x4 once again. We're going to end up with 2 channels, but these channels dimensions are going to be 4x4 once again, because we've defined kernel size and padding as 3 and 1. And I've actually forgotten something. We have an average pool right here, but we do not have any bias for our convolutions, but we want to make our final function for a neural network non-linear. For that, we are going to actually add some ReLU function. I'm just going to write it down and then explain it what it does. I'm actually going to use Alexey ReLU because I think it's better for some reason. ReLU 1, and we're going to have this ReLU for this right here, and we're going to have a third ReLU as well as a third pooling layer. Alright, so what does this ReLU does? I guess we can find some images on the net for a visualization. Yeah, so actually, well, we're going to end up with some kind of value after average pool. This value can be seen as on y-axis in this exact image. What Alexey ReLU does is that it well, essentially just how can I say it?
You maybe could show just a ReLU.
It's Alexey ReLU. It's Alexey ReLU.
Yeah.
ReLU actually, well, a simple ReLU is a bit different. It can be. I actually can see Alexey ReLU. Oh, just ReLU as well. So this is just flat in negative direction. So it essentially just modifies a value that that negative values are valued less than positive values, and that makes our output non-linear, and we want our output to be non-linear to like make some good predictions at the end of the day. All right, so we've defined our initialization function, and so what else? Let's define the feed forward function. Forward. It's going to take self, and it's going to take some input. And I think I just copy paste this code because there's nothing like really exceptional about it. I'm just going to change some values right here and explain it to you. So what we do is essentially we pass it through our first convolution layer, then we pass it through ReLU, and then we pass it through our average pool. That's actually it. And this is like a first call in our function. Then we do the same for like a second pool, second ReLU, and second convolution layer, and then for third. Then what we are going to do is actually flatten our output. So at the end, after we execute these three lines, we are going to get 2 filters one by one. So it's like a 3D array, and we want to flatten it. And then we want for that I use a flatten function. I have not defined it yet in my model, so let's do that pretty quickly. Solve.flatten should be equal to this. And after we execute flatten, we're going to end up with only like two values for our 2 classes. But then what I want to do is I want our neural network to show confidence in, well, in its predictions. So I want a number for each label. I want a number between 0 and 1, identifying how how confident neural network predicts that it is not this class, it's going to be 0, or is it this class, it's going to be 1. So if you have two images, like one image of a cat and other image for a dog, I want our neural network to show, for a cat image, I want to show it 0 for like a second output, let's say, and 1 for a first output. And for a dog image, I want it to show 1 for a second output and 0 for a first output, so that it is sure that a cat picture is a cat picture and a dog picture is a dog picture, not a cat picture. And for that, I'm going to use SoftMax function from PyTorch as well. I'm going to define it in our model as well. All right, I think that's it. I see. I already see a problem with our neural network, because I have hard-coded this output channels as 2 because I only have 2 classes right here. But we might want to create 3 classes or 4 or even more classes, and then we will have to modify our model all the time just to make up for these changes. This is not good, and this is why I want to pass, when I create like an entity of our model, I want to pass an out features label, and I want our network to to come up with not two values, but rather as much values as we want, as much values as we have labels. And
these functions, flatten and softmax, they operate with as many features as you need.
Yeah. Mm-hmm. That's correct. All right. I do also see how can we improve our model. So for sometimes, well, actually, I think, yeah, let's move on to, let's see the problems ourselves, and then I'm going to come up let's say with a solution to our problem that we are going to face further on. So let's leave it at that right now. It's a pretty good model. I hope it works. If it doesn't, we're just going to see what went wrong. So let's actually create another file, call it train.py. So we are going to train our neural network with this file. I'm just gonna import a bunch of stuff, and let's see what I'm importing. So I import Torch as well, first of all. Then I import a module called functional as f from Torch, torch.nn. I do also import optimization module. I do import our network from this model file that we've defined. So this net comes from this. Also, I have Torch summary to show like good and nice information about the training results. I do also import a module called TQDM, and you're going to see what it is down below when I actually train my network. It's just a nice line that just nice progress line. Let's put it like this. I do also import some transformations from Torch Vision Torch Vision package, and I do also import image folder from datasets, and data loader and CodeCut datasets. So there's like no magic right here, just a bunch of packages. So let's define our train dataset. So we have images, but we have to put them into dataset so that we can use them later on. Pretty easy. So train dataset. Let's actually write the string dataset. I think, yeah, we can just go with image folder. This is inbuilt within Torch Vision package. This helps us import our images easy into a dataset. So we don't have to write some custom functions. We already have one provided by Torch Vision. We are going to set root as, well, actually, what image folder expects us to pass into it is a structure like this. So it's from official documentation. I can make it a bit bigger for you so that you can see it better. Image folder actually wants our project structure, our image structure, to look like this. So we have some root directory, and we have, let's say, for example, a dog, but it can be like any class that you want. And under this dog directory, we have a bunch of images of dogs. And under cat directory, we have a bunch of images of cats. But let's see how our structure looks like. Well, we have a one. Well, it's actually, it's actually pretty good. So we have a class, and then under this classes directory, we have a bunch of images. So it's good. But what about test and train directories? So we have to split our images. We want to train our neural network on some images, and we want to test it on some other images that this neural network has never seen before. How do we do it actually? For that, we need another structure for our images, and it's actually it's essentially going to look like this. So we have some, let's say, images, and under images we should have two directories called train and test, and they're going to load into our train dataset images from this directory. So how do we do it actually? And under this train directory, we're going to have like some labels. Well, for example, like a one or a square, and under these directories, so under one and the square, we are going to have our images. So let me try to recreate it. So train one, new folder, square. So under square, we are going to have two directories called the one and square. Well, well, I spelled it wrong, but never mind. And under these directories, we will have these images. And we can do that manually if we want to, but I want to, automate this process because, well, I might want to generate other images, and every time put them in these directories is quite a headache. And I have to manually split our images into test and train sets. It's just, I'm lazy. I'm just going to write down some code to do it for me. So let's leave our file called train.py for some time, and let's create another file called prepare images. Prepare images.py. It should be a Python file. This is not going to be hard to do. Let's import some packages first. So I'm importing make directory method and list directory. Join is join path. Remove tree is actually a remove directory, but it also removes other directories under the one that you specify. We do also import copy and shuffle from random. All right. So first of all, let's cycle through every label in our created images directory from in this directory. and it is created images. So for each label directory in this folder, what we are going to do, that's all, we're going to define a label path, join path, created images, and the label. So we have a label path, that is good, but I want images paths from this directory. So what I do is images paths equals actually just list directory label path. All right, and just well, let's actually try it. I guess we can create a Jupyter. No, let's not dive. Let's not dive deeper than that. Let's actually just print our images path and see what's wrong with it. So Python prepare images. All right, let's see what we have. So we have images from our directory, but you see, these files, they are called the same. I want like a full path to these files, not just a relative path from a class directory. And for that, I'm just going to actually add a label path to these files. So I'm going to do it like this: join path, label path, and file name. For file name in this array that we've just got. All right, and let's see the result. This is much better. So right now, now we don't just have like this file name, but we have a complete path to this file. This is good. This is gonna help us later on. All right. So we have our images path, and I guess let's cycle through them. So for each file in oh, actually no, we've already done that. First of all, let's shuffle. Let's shuffle. Shuffle. Oh my god, I cannot spell it. Let's shuffle our images. Just because you know, if you try to generate images with our application called image generator, I mean, it's completely fine to just you know, paint or draw them, save them, but after some time you might get a bit, you know, maybe tired and write it like this and like this, and we want to shuffle these images just to make our whole data set, you know, so that our final data set actually is, you know, does not differ much from one end to another end. This is why I'm just going to shuffle them. All right, let's define test images length. No, first of all, we'll have a length images path, and this is an easy way to split our actually sets of images. I can take our images path. Oh, actually, it's length of images path. Yes. So I take like our whole number of images and multiply it by some value that is less than 1. Let's say, for example, it's 0.2, and I'm going to get the amount of test images that I want to use. So for example, if I have like a total of 100 images, I want to have 20 for them as test images and 80 of them as the train images. But this code is quite wrong because we can end up with not a whole number of test images. For example, if we have here like 13, yeah, number of 13, and we multiply it by 0, 0.2, we are not going to get an integer, but we want to get an integer, and for that I'm just going to wrap it in integer function method. And after that it's pretty easy. We are going to define the test images from actually, and its images path. I'm going to split this array like this. Test images length, yes. So what this do is actually, well, we have an array for our paths, like all amount, every path that we have is in this variable right here in this array. And what I do actually is I take, I actually slice this array from the zeros element up to this element right here. So if we have like 100 images, I take images from zeros index up to 20s. Well, actually, yeah, up to 20s, but not up to 20s, but rather to 19th. if you
You know what I mean?
you know what I mean. All right, and you also want to have range from. And this code is exactly the same, just we take images from this index up to the last index. Then what we want to do is to actually copy them. We could make like symbolic links and stuff like this. I don't know how it would work on Windows actually. Maybe it's going to work just fine, but let's just copy them. We don't have a lot of images and their sizes are like minuscule. So let's define a test2 directory. Well, it's quite easy. We're just going to join path. But where do we actually save it? We have this directory right here called created images. Let's maybe have another one called, or maybe sorted images. And under this directory, we are going to save all our like other files. All right, sorted images. Actually, I wonder. Well, we don't want to save our test files to sorted images. We want to save them under sorted images /test directory. I wonder if this is going to work. Maybe not actually, but let's try it out nonetheless. And we are going to join it with our label, and then we have to make this directory just in case it doesn't exist. Maybe it already does, but who knows. And then for every path in our test from paths, we copy from our original place to our destination. test2 directory, yeah. And the same applies to train images as well. So train2. I don't think it'll work out, and we have to tinker a bit with this, but let's see how it works first. Train from and train2. So let's see. We cycle through each label we get paths under each label. We shuffle the images. We define the amount of test images that we want. We define where we want to save our images, and then we just copy them from one place to another one. All right, let's see how it works. Oh my god, no! I deleted the wrong. No!
Oops.
Would you like to undo create sorted images? No, I don't want to undo it. What went wrong? Sorry, I'm just going to restore it from my from my trash. Restore it.
Oof.
Restore it. All right, saved. What I want to do is just delete this directory. So we did not have it originally, and I hope we can create it with this line right here. All right, let's try it out. God, where am I? Python for images. All right. So it did create this directory, and yeah, well, actually everything went just fine. Yeah, it worked. So we have sorted images, and under this we have a test and train directories, and under this we have any images. But under test we don't have any images yet, just because, well, we've defined that every fifth image essentially is going to go into test, but we do only have 4 images under one and 2 images under square. So for that we want to create a bit more images. So let's generate them actually. Python image generator. We already have 4, and I want to add like a few more. Let's go up to 10.
Express drawing.
Yeah, thanks. And the same applies for a square as well. We do already have 2 squares. I just want to make a bit more. You know, it actually looks more like a rectangle, not a square, but alright. But a square is a rectangle nonetheless, so I think it is fine. Alright, so we have 10 images under each class, and then I want to run the same script once again and see. So under test we have 2 images for one and 2 images for a square. Yeah, that's expected. So every fifth image goes to test, and under train we have 8 images. So it's 1, 2, 3, 4, 5, 6, 7, 8. 8 images here and 8 images here. All right. Woo, that's good. So we do have our images sorted. Let's go back to our train script. I hope I can write a bit more before our session ends in 7 minutes.
Wow, it's not that strict.
Yeah, it's going to be a trilogy.
Yeah.
All right. Let's just let me just find. Yeah, left. So root for our image folder data loader is going to be sorted images /train. What else do we want to define? We actually want to define a bit of transforms. So trans. Did I spell it wrong once again? No, it's fine. What transforms we want to have? Well, our images are saved in .png format, and well, in PNG format there are like 4 channels, one for red, one for red, one for green, one for blue, and one for alpha. But our image is grayscale, and we only want one channel. And we actually want to convert our image into a tensor, just to pass it through this data loader. So for that, let's define our train transformations. Oh, it's actually transforms. It's shorter and it's much better. So we want to compose a few transforms. First one is going to be grayscale. So we want our image to be, well, to be converted to a grayscale. That doesn't do much, but it just helps helps to convert it to tensor. So yeah, like this. We transform it into a grayscale, and then we convert our image into a tensor. Why doesn't lint work? Linter doesn't work for some reason. Did I import it? Yes, I did import it. That's strange, but it should work. Train transforms. All right, we do have our train dataset. We do also want our test dataset to be loaded. So test dataset is going to be exactly the same, actually. And since transformations are the same, I think we can just call them transforms, just so that we don't repeat ourselves. All right, let's move on. We define train loader, and we pass it our train dataset. We also want to define a batch size. What batch size is well, actually, we have a lot of like images. We have a lot of input data, but sometimes we don't want to correct our predictions, correct our weights and biases, just for a single image, because sometimes it is faster to make like a bunch of predictions first and accumulate the amount of like error that we have, and then for this whole batch we identify like the amount of correction level that we want to get, and it actually helps us to train our neural network faster, but it comes with a downside that we search our local minima for a function much more chaotic. I think I can show you an image actually. Oh no.
Ooh.
This is not it.
Stochastic money.
Yeah, I think this image explains it better. I'm going to use stochastic gradient descent later on as well, but same applies for batch size. If we want to correct our like weights and biases image by image, our path for searching the local minima is going to look like this. So it's going to be like a lot smoother than if we want to use like batches, but it's going to be faster if we use batches, and they're going to end up with the same outcome nonetheless. So yeah, that's it. So so let's define our batch size. I think, well, right now we have like so few images. We have only 8 images to train with. We don't actually need like some great amount of batch size. I'm just gonna put it to as 1. But then we come to another problem. We have two little images to train from. So we have only 8, and it is not enough. What we can do is that we can somehow tweak, somehow modify our images. Right here, for example, we can rotate them, or we can shift them slightly in some direction, for example, up or down, left or right. We can even scale our image. So, for example, a smaller square is a square. A larger square is is a square as well. Same applies to 1 as well. For some images, we can mirror. For example, if we have a square, we can mirror like horizontally or vertically and still end up with a square, but inputs are going to be slightly different. It's going to be a square, but it's going to be like a different square. And this whole process multiplies our training data like a few times. And I think I'm going to implement it in the next session because we are out of time. So
Perfect
thank you
timing,
for
Alex.
listening to me, Igor. I'm passing the word back to you.
Yeah, thanks a lot, Alexey. That's again super impressive. Like you implementing everything from scratch. I don't even remember when or if I did something similar before. So really super impressive. And I'm looking forward to the third session. So I don't know, maybe a fourth as well. Let's see.
Yeah, we'll see. We'll see.
Yeah, but anyway, it's a great project of yours and very cool. And also, you have a telescope behind you. Are you a fan of astronomy?
Yeah, I'm a big fan of astronomy actually. I just don't do it that often. Well, it's a small telescope, and after all, you can only like see the moon.
Well, only. So maybe one of your future talks will be about this as well.
I don't know. Maybe.
Let's
Right.
see.
So bye
But
bye
yeah,
then.
thanks a lot. Yeah, have a great Saturday. See you soon.